So here is a possible solution, and this solution illustrates actually a very important theme, randomization, that we'll be encountering quite a few times in very different contexts in different networks this course. This is the very first encountering of that randomization idea. It says that, you know what, if you're on a particular web page, a node in the graph here, you may be hopping to the other nodes that's hyperlinked from this node with evenly likely chance. For example, if there are two of them, 1/2, 1/2. But this whole behavior may be only theta% of the time you follow. And 1 minus theta, where theta is just some number between 0 and 100 in percentage points, the other 1 minus theta% of the time, you actually will do a random flipping of the web pages. Okay? So following the embedded outgoing links is only part of the model of the navigation behavior by users on the web. It represents, say, theta%, and 1 minus theta%, you will be doing a random picking. It turns out that what theta you pick determines quite a few things, including the rate of convergence. Smaller theta gives you faster convergence in general, but smaller theta also means that you are pretty much ignoring the connectivity pattern of the hyperlinked graph. So that's not too surprising. It turns out that we tend to pick 85% or 0.85 as the right trade-off between relevance of the connectivity pattern and the speed of convergence. So how do we model, back to this random flipping of web pages? Well, we're saying that here's a big matrix, which is really 1 over n, 1 over n, 1 over n, 1 over n, dot, 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 and 1 over n, 1 over n, dot, dot, dot. And every single row is just 1 over n, which we can write as basically a matrix of 1, 1, 1, 1, 1, 1, 1, 1. Everywhere is 1 divided by n, which we can write as simply 1 over n times a vector of 1, outer product with a vector of 1s. Again, outer product may sound a little weird to you, but you can write out a simple example, say a two-dimensional example. Okay, 1, 1 is a column vector, outer product with 1, 1. So 1 by 2 times 2 by 1 times 1 by 2. You get a 2 by 2 matrix, which is 1, 1, 1, 1. Okay, so 1 outer product with 1 column, then row vector normalized by 1 over n is exactly what we want. So the third matrix is simply 1 minus theta times normalization 1 and this matrix of all 1s. Vector 1 outer product with vector 1. And then don't forget the original theta% of the time. You will follow h, or better still, the modified h hat. And this plus this is what we call the Google matrix, represented as G. Now don't get confused with the Gij back in lecture 1 in cellular network. Okay? That can also give you a matrix G. There are interesting, striking parallels between the two, but not stemming from the confusion of the symbols they use. So this matrix G, the Google matrix, is the sum of two matrices. We know this matrix is nice because it's the sum in turn of H, which is sparse, and a rank 1 matrix for the dangling nodes. And this obviously is a rank 1 matrix as well. It's a very simple matrix. So G is the sum of a large and sparse matrix plus two large and rank 1 simple structured matrix.